Hello everyone, I'm Rohit here, and in this video I'm going to talk about higher dimensions. So what are higher dimensions and what are strings, and can DGR give us a clue about that? So I am basically author of this book, Decoding Gravity, Time and Causality, and it is basically explaining or describing a new theory of everything and a new theory of quantum gravity called as dynamic general relativity. So without further delay, we'll just so this is the book. Basically it will be available internationally soon, and so this higher dimensions and strings, before I start the video, I would say that whatever I am going to say today, you will have to take it with a pinch of salt, because DGR is just giving us a clue or a hint of what additional dimensions or higher dimensions may be and what strings may be. So I'm not claiming that this is absolutely 100%. We will have to do a lot of further research, and then only whatever I am going to say may be confirmed or refuted. So whatever I am saying are just possibilities. Okay, and I'm just saying it how DGR explains what are strings or what are higher dimensions. Probably, so we don't know yet. Okay, so we'll just see. Initially, I'll just explain what exactly is higher dimensions. So we are basically living in a three-dimensional world. Three dimensions means what? That we need for any particular point in space, we need three axes. So one is the x-axis, the y-axis, and the z-axis. The z-axis is going right from out of the paper inside to the inside of the paper, like that. So three dimensions, three axes we need. So any point where it is can be influenced by three factors basically. So it is the x coordinate. If we keep varying, if we keep the y coordinate and the z coordinate the same, but if we keep varying the x coordinate, if any small change in the x coordinate happens, there is a change in the position of the y the point. So even if the x and even if the y and the z coordinates are same, any change in the x coordinate influences the ultimate position of the point, location of the point in three dimensions. So what is basically this dimension? It is basically anything which is influencing the location of the point. So we can be pretty confident about this in a three-dimensional world. In a three-dimensional world or three dimensions, what is basically happening is any change in the in one coordinate has some influence on the ultimate location of the point. So if only the x coordinate of a particular point is changing, then it will have one particular effect on the location. So if the point is here and only the z coordinate changes, the x and the y coordinate remains the same, but the z coordinate changes, that means what the point will go inside or outside of the page. So in a similar manner, if only the x coordinate changes, then only the point will keep staying in one particular z and y coordinate, but only it will change the x coordinate. So like that, you have to understand that any change in any of these three dimensions, coordinate axes, is basically causing a change in the ultimate location of the point, one point. So we are talking only about one point over here. So actually it's said that it is very difficult for us humans, because of our ignorance, to imagine higher dimensions. Before the one dimension, actually zero dimension also comes. A single point is a zero dimension. But if you have a three-dimensional axis and there is one single point, this is not zero dimension. Zero dimension is what? Point and nothing else. The whole coordinate system is within the point. So that is a zero dimension. So zero dimension has a little role actually over here. So, but if there is one point and we want to have higher dimension, we want one-dimensional entity. So we double the number of points. So 1 point becomes 2 points. So 2 points forms a line. So if 2 points form a line, this becomes a this becomes a one-dimensional entity. One-dimensional entity, that is line. So it has only one dimension, that is only maybe x coordinate or maybe only y coordinate, like that. So it has only one coordinate. It needs only one axis. So there is only one thing which can influence the change. So if there is any change in the x axis in this one-dimensional line, there will be a change in the ultimate location of the point. So there is no y and z axis in this one-dimensional line. So what about two-dimensional? So if you have we have 2 points, but we want not one-dimensional, but we want two-dimensional. So what we do is we double the number of points. So we had 2 points, now we'll have 4 points. So 4 points, we will get a square or a rectangle or whatever you want. So square, we will just take up a square. So if you have a square, then we have two axes basically, x axis and y axis. So there are 4 points. So each point will have a particular x coordinate and a particular y coordinate. But so these, there will be two influences basically. So if you have any change in x axis, x coordinate of a point, but y coordinate remains the same. So x coordinate changes. So there will be a slight change in the ultimate location of the point. So you can understand that these points initially they were a particular square, but as soon as the left up corner point, or maybe let's say A, this particular point, the x coordinate changes, but y coordinate remains the same. So what will happen is that x coordinate has influenced the ultimate position of the x coordinate of the square. So so this particular vertex or the corner, left up corner, only the x coordinate is changing. So what is happening is that the square is no longer a square. Now it has become a different shape basically. So the square is no longer a square. So here in a two-dimensional entity, there are how many influences? 2 influences. So in a three-dimensional, there will be 3 axes, x, y, and z axis. So there are 3 influences. So if you want to basically change the location of a point, you can do it by changing its x coordinate or y coordinate or z coordinate, like that. Anyhow, so if you had two-dimensional, you had basically a square with 4 points. Now for getting the three-dimensional entity, what we have to do is have to double the number of points. So from 4 we come to 8 points. So 8 points we get from a square, we basically get a cube. So it's a three-dimensional entity, a cube. Now this is very simple actually. Most of them will be able to understand this very nicely. There's no problem. So this cube, again, the same things have basically that there are three axes, x, y, and z axis, and there are 4 plus 4, 8 points. So if there are 8 points, so we have doubled the four points which we had in the square. We have doubled it to get 8. So each of these points, the location of this point can be defined with 3 coordinates, and each of these axes can have influence on the ultimate location of the point. So if there is any change in the x coordinate or y coordinate or z coordinate of the point, there will be a change in the position of the point. Now we have 8 points and we want higher dimension, so 4-dimensional we want. So with these 8 points, we have to double them again. So 8 points becomes 16 points. Now this same thing continues basically. So 4 dimensions, then 5 dimensions. You what you do is, from 8 points you get another 8 points. That is 8 plus 8, 16. So double the number of points. Then 5th dimension, you again double it. So 16 plus 16. Anyhow, this will keep going. So this way you can define a 4th dimension or 5th dimension or 6th dimension or 7th dimension. But ultimately, it's a very tricky thing how exactly to till 4th dimension. It is easy to understand. So maybe there is a cube basically, and 4th dimension is the time. So we can define exact positions of all the 8 vertices or corners of the cube. And now 4th dimension, for defining the 4th dimension, we have to define time or the arrow of time. So let's say in DGR sake, we have a time or of Planck time. So we want to understand what is the evolution of the locations of each of these points. Let's say let's name these points A, B, C, D, E, F, G, H. So A has some location in the 3-dimensional coordinate system. B has a location, C has a location, D has, every point has a location which is basically defined by 3 coordinates. Now, once the first Planck time is over, the location of A might change. There might be some change in the x coordinate, y coordinate, z coordinate. So each of these points, the location will ultimately change. So, so the cube may not remain a cube. So it may distort. It may become a parallelogram, or it may become a rhomboid, or it may become some another shape. Okay. So at the end of the first Planck time, we get again another 8 set of points, but each of these points will have a different coordinate location. So we can define that there is a change in the coordinate locations of each of these points. So 8 plus 8, 16. Then again the second Planck time comes, and again we can have another 8 points. So we can keep seeing that this was a cube, then it became a parallelogram, then it became a rhombus, then it became a diamond, then it became a distorted cube with some different shape. So like that, the 4th dimension can also be very nicely, very easily defined, and we can basically imagine it. But after the 4th dimension, it becomes a bit of a difficult thing. 5th dimension, 6th dimension, 7th dimension, it's a very difficult thing. But this is very basic actually. But nobody is able to define basically after 5th dimension. But you have to remember the influence actually. So the 2-dimensional line, only one axis is there, and in this axis any change in the x coordinate will influence the location, ultimate location of the point. In 3 dimensions, there are three coordinate and like that. In 2-dimensional there are 2 coordinate axes, and in 3-dimensional there are 3 coordinate axes, and each point will have 3 dimension the coordinates. So x coordinate, y coordinate, z coordinate, and fourth will have again the same. So every Planck time there will be a change in each of the coordinate locations of the 2 points. Now what about the 5th dimension? Like that, if in a 5-dimensional, so now from here the string, the questionable part comes. Now from till here everything is well defined in mathematics and string theory and whatever. So till here we are sticking to the book, but after this, whatever are my thoughts, they are starting. So here again 3-dimensional and 4-dimensional. 4th dimension, again there are 3 axes, and there is a 4th axis of time. So every jump in the Planck clock, there could be an additional change in the XYZ axis. So every jump in the, or every change in this 4th dimension, 4th dimensional axis will also have a change in the ultimate location of the point. So here we can add a 5th axis, which is basically also an influence basically. So it can influence the ultimate location of each of these points. So ultimately we have 4 dimensions, and these are 8 points, but the 4th dimension, in the 4th dimension we needed what? Another 8 locations, the new locations of these points. Now the 5th dimension, again we want another 8 points, which are, so we are basically doubling the points. So initially we had 8, then we had 16. Now again doubling, and this 5th dimension, again what it does is it causes influence on the ultimate location of each of these points. Now again the 6th dimension, again same thing happens. We have an influence on the ultimate coordinate location of each of these points. Okay, and we are doubling the points, doubling every time we are basically doubling the points. 5th dimension, 6th dimension. Okay, so for now you have to just understand that the axis, as many number of axes are there. If there is 1 dimension, there is 1 axis. So each change in the coordinate location of that axis has influence. So 2 dimensions, 2 axes, 3 dimensions, 3 axes, 4 dimensions, 4 axes, 5 dimensions will have 5 axes, and 5 axes means what? The 4 axes which we have already discussed, that is 1, 2, 3, and 4 dimension of time. But 5th axis will also be there, which will also have an influence on the ultimate location of each of these 8 points which we are interested in. So we are interested in only 8 points, but the points will keep evolving, and how the points evolve is basically dependent on one more influence. So there can be multiple influences. So time is one influence. So there are other influences also. So the ultimate location of these points can be, so if there is not one influence but multiple influences which change the ultimate location of the points which we are interested in. So this A, B, C, D, E, F, G, H. So they can have 5 dimensions or 6 dimensions. So as many influences are there, as that many number of dimensions you can have. So what are strings? If you ask a string theorist what are strings, they will say that basically they are a 1-dimensional entity, and they are basically vibrating in a multiple dimensional or maybe 10-dimensional or 11-dimensional hyperspace. which is itself a very difficult thing to imagine for us. Calabi-Yau manifolds, so which are the shape of which determines the property of the particle, but the shape of it can have 10 to the power 500 different possible shapes. So what are strings? They can be open strings and closed strings. So these are the typical answers basically. So we will keep digging. What exactly are they made of? We don't know. So this is a wrong question. So this particular question, they will say either we don't know, or it's a wrong question, or they are basically strings basically. So everything is made up of strings. So we cannot, this question is itself wrong. So we should not ask this question. So these are the typical answers of some will give one answer or some will give another answer, but basically nobody knows what the strings are made of. But actually we know we know in a way what the strings are made up of. Strings are basically at the core of every particle. And we know from Einstein's E is equal to mc square that every particle with mass has what? Every particle with mass has energy in it, very high amount of energy stored in it. So the strings must be energy definitely. So, but that doesn't help actually, because the contemporary physics says that energy is energy. But what exactly is the energy made of? We don't know. We don't know that. So energy is made up of what? We don't know. Now there is a bit of a clue here actually. In dynamic general relativity, energy is basically two types: positive energy or negative energy. And positive energy is what? Destruction. Negative energy is what? Active creation. So unit of energy, or the smallest bit of energy, is T is equal to 0 compartment, and negative energy is T is equal to T max compartment. That apart, but energy has a very proper definition in DGR. DGR says that any deviation from universal time, that is, if the time deviates from universal time to local time, means any place where there is a deviation from the universal time is basically energy. Which means what? So if there is a active creation and destruction which is balanced at any place, then there is no active expansion or contraction of space. So if there is no active expansion or contraction of space, there is zero energy. So if there is any change in the shape of a particular zone or region, that is energy. So any change in the time, local time, is also energy. Which means that if you have a place where there is a gravitational time dilation, that means that is a zone of positive energy. If there is a gravitational time contraction, then if there is a time contraction basically, so it is a negative energy. So there is a very good definition. Now this space active expansion and contraction is basically fluctuation, and there is a fluctuation of time. So this LIGO, detection of gravitational waves of LIGO, had a clue in it that energy is equivalent to any fluctuation in the space and time. So there is a fluctuation in the space and time. So active expansion, active contraction of space and time. So there is an active expansion, contraction, which is basically space and time, which is fluctuating. So strings, what are strings made of? They are made up of space-time fluctuations. So okay, what is string theory? Initially, string theory was a theory meant specifically to define particles. So it was a theory for made to define what particles are. So a standard model, all the particles are made up of one particular string, which is basically vibrating in a particular mode. So that's what the string theory started before. Initially, it was not an intention to give a quantum theory of gravity and all. It only intended for explaining all the particles and their properties. But the mathematics basically they thought that it is able to explain all the gravity and graviton and all that as well, which is a good thing actually. But they don't understand what the mathematics is telling them. That's what is the claim. So the mathematics is really good and really beautiful, and there is reason why they have to pursue it, which is a good thing actually. So it must be having some clue or the other. But basically, string theory was a particle theory. Okay, so a particle in a string theory is basically vibrating strings. So a particle in DGR. What is a particle in DGR? DGR says that a particle is having a energy which is condensed in a very small place, and that energy is basically positive energy. So positive energy is what? Destruction. So there is active destruction going on at the core of the particle. So there is EPCA formation all around it. So the EPCAs are going inwards and inside the particle. So there is definitely some space-time fluctuation going on around the particle. That is okay. Now, further defining of the particle. Now, actually speaking, particle has, we know that all the particles have not only one property of mass, but it has a huge number of properties. Like it has a spin, which we don't know what exactly it is. The contemporary physics cannot explain it. DGR can explain it very nicely, but I'm not going to go into details of how, what is a particle, what is the shape of the particle and all that. But it has basically momentum, it has kinetic energy, it has spin, it has multiple numbers, strangeness number, and all those things. So the particle in DGR is much more complex actually. Now, general relativity can explain, at least to some extent, how is the geodesic around a ball, or maybe because around the earth, because of the mass of the thing. So the Einstein's field equations are basically telling us how the mass of the this thing changes the shape of and time of around the ball or around the earth. But unfortunately, general relativity cannot explain what is the geodesic around a particle, because it's not a quantum theory basically. So it cannot give any indication, but DGR can give, and it is giving very detailed, even at a very the DGR is basically in infant stage. It is not very highly advanced in a very highly advanced stage as yet. But even in this particular stage, what exactly would be the geodesic around the particle, and how would be the spin of the particle? Everything will be explained, at least phenomenologically, and at least in short or in brief, or you can visualize it like that. So geodesic of around a particle, it can give clues to how would be the geodesic around a particle. Okay, so it is basically what is the space-time curvature, and how the space-time curvature around a particle changes. Now imagine that there is one particle, let's say a quark, and we know that the quark is basically within the nucleon. Maybe let's say this particular nucleon is a proton. So we know that there are not one but three quarks within this proton, and there are multiple gluons also within it. And this quark is basically moving very fast. So we are basically defining a particle. So we want to define the geodesic around the particle. Okay. So let's say this particle quark is Q, and let's say that there is one particle over here, quark. It's moving very rapidly near the speed of light, and it's an influence of multiple things. So the particle is under the influence of multiple quarks within. So this quark is there. There are three quarks basically, 1, 2, 3. So we are basically interested in this quark, Q, and P and R are also other quarks. So these quarks are also influencing this particular quark. So there is one influence, two influence. Now this particular quark is also under influence of other quarks in the surrounding neighboring nuclei. Okay, so neighboring nucleons basically. So there is a neutron, there are two neutrons around it. There are some quarks which are there, which are also influencing this particular quark. So there are multiple influences which it has. So let's say this particular Q is there, and just outside it, we imagine a cubical space. This is not, we're not imagining a Planck compartment. We are basically imagining a small cube, maybe a nanometer size or maybe a femtometer size cube. Femtometer size cube. So 1 femtometer space time is there, which is made up of multiple Planck compartments. Planck compartments are extremely small, so they'll be made up of multiple Planck compartments. 10 to the power 35 is the size of a Planck compartment. So a femtometer cube will have multiple, very high number of Planck compartments. So we are just imagining a quark is there, and just outside the quark there is a small cube, and what we are trying to imagine is what will be the influences on this and how we can define the geodesic of this particular the space-time in this particular cube. Now there are multiple influences which can have. So each of these quarks, like let's say this is a Q quark, so P and Q, P and R. So there is a lot of destruction going around, okay, inside the particle, which is causing EPCs and which is causing the space-time to form cubical, the spherical aggregates of Planck compartments which are going inside, and which are basically, you can imagine that. So Q is there. So the similar thing is happening in P. Similar thing is happening in Q, and each of them is basically causing the space-time to deviate over there. So there is one influence of P, there's one influence of Q, there's one influence of R, there's one influence of other neighboring particles. Now there is this momentum. So momentum means what? This particular quark is not at rest, actually. It's moving. So it's moving. So its EPCs which are going inwards are basically, there's an asymmetry of this thing. So this asymmetry can also, now this whole proton is also having a spin. This quark is also having a spin. So the spin of the proton can have influence on this particular geodesic or what cubical space. So the momentum of the quark can have, the momentum of the quark can also have. So there are multiple things which actually, there are multiple influences. So this momentum can influence EPCs, and then the spin can influence. Then okay, so there are many other influences which can happen. Like there is we know that, you know, even Andromeda galaxy is a huge galaxy and it has a huge mass basically. So each of the stars can send linear EPCs. So all the linear EPCs combined together from linear Andromeda galaxy can actually influence the location, this particular small cubical space. Even the linear EPCs from the mass of the universe, the entire universe can actually influence this particular. So basically, there can be multiple influences on this small particular cubical space. So to define the geodesic and how the geodesic around the particle evolves is a big question, actually, a big question, and there will be multiple influences which we have to take into account to understand this. Okay, so let's say that this particular cube is there, A, B, C, D, and E, F, G, H. 8 points, they are forming the cube. So this is the femtometer cube which we are interested in, which is basically very close to this quark which we are thinking of. So there it is under multiple influences. Now, let me say one thing, that these images are just completely diagrammatic. So I have very little means this you have to just uh, look at these images only for understanding purposes. Beyond that, nothing, because these are almost definitely wrong. That this so you can understand that the first at the first instance of time, this is the shape of the ultimate, the location of the first initial location of A, B, C, D, E, F, G, H form a cube. Okay, so with first Planck clock of universal time, there is a change in the ultimate location of the A, B, C, D, but E, F, G, H remain the same. This is just you can say, assume that one particular influence is happening. So one EPCA is pulling these only these points in that direction, but these points are not yet involved. So this whole cube is moving in this particular direction, but these are the same basically. So first influence is happening. The first factor is basically changing the geometry or the geodesic around the of the cube. Now again, now you can understand that this can also happen, that it's the first Planck time, the multiple influences can happen. So this particular location of A, B, C, D, E, F, G, H is, we are getting it by considering the first influence. So there are 5-6 influences which are basically potentially going to change these A, B, C, D, E, F, G, H. Now we are considering the first influence only. So the first influence causes A, B, C, and D to be here, but the E, F, G, H will remain constant. But what about the second influence? The second influence, the Planck time has not ended yet, but the second influence also is happening. So first influence causes the cube to become this, the second influence causes this to become this. So 8 new locations for the first influence, then 8 new locations for the second influence, then again 8 new locations for the third influence. So this particular new shape which was created by the first influence is now changed to second shape because of the second influence. Then the second influence changes to third influence. Third influence changes to fourth influence, like that. So basically we have to so like this, if there are 8 influences or 9 influences or 10 influences, we don't know how many influences. So all these 8 influences can change the ultimate geodesic or the ultimate location of these points A, B, C, D, E, F, G, H just outside the quark. So you can understand that the additional dimensions which are spoken in string theory, and so you can understand that the space-time fluctuations are basically energy, and the space-time fluctuations are fluctuating in a unison or in a particular manner, which is repeating, self-repeating, and these space-time fluctuations are basically energy, and these space-time fluctuations have multiple influences, not one, not two, but multiple. And these multiple influences will basically create space-time fluctuations which are having an influence of multiple. So basically, the more the number of influences, the more the axes which we need to ultimately understand what is the ultimate location or what is the ultimate shape of the geodesic in that particular area. Now these are very, very diagrammatic images. I don't want you to take these as basically anything. These are only to understand what I am trying to say, that the higher dimensions in string theory could be due to the excessive influence of multiple other things. And you have to basically not only you have to read the book, but much more work is needed to actually understand how the geodesic around the particle would be, and what are the influences, and what are the ones which form higher dimensions. Means what we can understand 3 dimensions and the 4th dimension of time, but the 5th, the 6th, the 7th, the 8th, the 9th, the 10th, the 11th, now all these things, what influences which each of these dimensions indicate, we don't know that yet. And what exactly is the mathematics saying, I won't be able to have any idea unless I have a knowledge about the mathematics. So this basically enigma can be solved only in collaboration with those who know or understand the mathematics of string theory. So that is the reason why, the one thing is clear, that DGR can actually have a very important influence in how string theory and the mathematics of string theory progresses forward, because it can definitely put a limit to what number of so because 10 to the power 500 is a very exuberantly big number. But if DGR can limit the possible variations, then it can definitely do a pretty good job of uniting string theory with loop quantum gravity. And I think that the mathematics of string theory, it may be just 10 to the power 500, maybe just something which is wrong, basically, because we don't know the limits. And that's why DGR could be of extreme help. Rather, progress of DGR could be dependent on utilizing the mathematics of string theory. That is why string theorists have to read DGR and open up their minds. And I do believe that that is the reason why DGR can give us clues on what are additional higher dimensions and also what are strings. I would suggest that you buy the book and read the book, and also subscribe to the channel so that you don't miss the videos. And also I want you to have a look at all the psychology related videos. So thank you very much for your attention, and bye bye, have a nice day.